sit wherever you want. So the last on Monday, we stopped at one of the eye clickers, which is asking which of the following is polar. So in all the cases that we touched based on, they were in a certain structure, either AX4, AX2, AX2E2, and from there we figured, based on the table and based on our knowledge of which is polar and which is not polar, we decided whether they are polar or not. In this case, it's harder. It's not as easy as figuring out it is AX2 or AX3. So in this case, what we're gonna do, we have to assign the dipole moment. We said that the dipole moment usually goes from the one, or always goes from the one with the low electronegativity to the high electronegativity. In this case, the arrow, which is the dipole moment, gonna go from the carbon to the Cl. Why? Because Cl is more electronegative than the carbon. In case of carbon-hydrogen, the hydrogen is less electronegative than the carbon, so it's going to go this way. So as you can see, one time the carbon is more electronegative, the other time is less electronegative. It's relative, it depends what I'm talking about, or relative to what. The same case in here is going to be this, and then the hydrogen to the carbon. Now, I'm sure that most of you know that, or all of you know that if I have two vectors which are consecutive, the addition of them is going to be something, a vector like that. So the addition of those two is going to be this one, and for those two is this one. So this is the total dipole of both. They are of equal magnitude, of equal vector size, because the elements are the same and they are opposite to each other, so the dipole moment equal to 0. The dipole moments cancels out. Therefore, since the dipole moment equal to 0, that means this is a non-polar compound. Okay, let's see what about the other compound in here. So this is called the trans compound. A trans, and all what it means by trans that the Cl's are on different sides of the compound. In this case, it is a cis compound because the two Cl's are on the same side of the double bond. Okay? So in this case, this is the dipole moment. And from carbon, it's going to be from hydrogen to carbon because hydrogen is less electronegative than the carbon. And the same case in here. And the same in here. So in this case, we have two dipoles. The addition of the two vectors are going in the same way. So therefore, the dipole, the sum of all the dipole moment of those two vectors does not equal to 0. And since it does not equal to 0, that means this molecule is polar. Okay? So this is kind of a special way of looking at it because it is harder than just assigning AX2, AX3, AX4, or AX2E2. In this case, where I have exactly the same compound, the only difference is where are the Cl compares to the double bond. I have to think about it as vectors. Now with this, we're done from the polarity. We're going to start a little bit new topic, and it is one of the very important topics in chapter 8, which is the formal charge. So, first of all, I'm going to teach you how to calculate the formal charge, and after that, I'm going to tell you the importance of knowing a formal charge. So the formal charge, the equation, or how to calculate a formal charge of an atom, definitely we're talking about an atom in a compound, equal the number of valence electrons. In other words, if it is the group in which the atom belongs to, minus the LPE, which I explained it in here, which is the number of electrons in the lone pair electrons on an atom, plus half, and I just want to point out that the brackets is for both, and the minus is outside the bracket, so that's going to be minus for the whole bracket in there, the bonding electrons, and plus half the bonding electrons, which are the number of bonding electrons around an atom. Now the formal charge, usually most of the time it is confused by the oxidation number. The oxidation number that we learned in chapter 3 is different, chapter 4 is different than the formal charge. The formal charge, we use this equation to figure it out. The oxidation number, we learned another method to do that in chapter 4. So it isn't, the formal charge is not the same as the oxidation number. So the easiest way to understand this is by doing examples. So I'm going to start examples of calculating the formal charge in different compounds. And I'm going to start with ClO minus. So this is how you need to draw the Lewis structure. Now I'm going to calculate the formal charge of Cl. So the equation says it's the number of valence electrons minus minus the LPE plus half the BE. So the number of valence electrons of chlorine, that implies the group in which the chlorine is. Chlorine is in group 7, that means it's going to have 7 valence electrons, minus the number of lone pairs around the chlorine, around the atom that I'm calculating the formal charge for. And it is 1, 2, 3, 4, 5, 6. I have 6 lone pairs electrons around the Cl. So I'm going to put 6 electrons. Plus half the number of electrons in bonding that are connected definitely to the Cl. We're talking about the Cl. The Cl have one bond. Each bond represents 2 electrons, so it is half the 2 electrons. And that implies 7 minus 7 equal to 0. That implies the formal charge on chlorine is 0. Now we're going to do the formal charge on the oxygen. Okay, again, the number of valence electrons. Oxygen belongs to group 6, so 6 valence electrons, minus the number of lone pairs around the oxygen. It's 1, 2, 3, 4, 5, 6, plus half the number of electrons in bonding. So I have one bond, 2 electrons, so half 2 electrons. So that's 7. So 6 minus 7 equal to minus 1. That means the formal charge on oxygen is minus 1. Now, always the addition of all the formal charges of all the atoms inside a polyanion or polycation or a compound should add up to the formal charge of the whole compound. In other words, 0 plus minus 1 equal to minus 1, the total number out there. Okay? So this is how we calculate the formal charge. I'm going to do one more example before I tell you why we're doing that. Why even we calculate the formal charge of something. And this is the second example. I'm going to calculate the formal charge of oxygen. Again, it's the number of valence electron. Oxygen belongs to group 6. So 6 minus the number of lone pairs on the oxygen, which is 1, 2, 3, 4, 5, 6, plus half the number of electrons in bonding. I have one bond, 2 electrons. So that's equals 6 minus 7 equal to minus 1. So the formula charge on that oxygen is minus 1. Now I'm going to go to the hydrogen. Calculating the formal charge of hydrogen. Hydrogen belongs to group 1, so the number of valence electrons is 1, minus the number of lone pairs around the hydrogen is 0, there is no lone pairs there, plus half the number of electrons in bonding, which is 2. That means 1 minus 1 equal to 0, and that makes sense because the addition of all the formal charges in this compound should add up to the total formal charge. Okay? So this is how we calculate the formal charges in any compound. The first thing, as you see, I have to write the Lewis structure. Otherwise, I wouldn't be able to calculate the formal charge. So if I give you a compound, and on both cases, I drew the Lewis structure for you. But for later on in any exercise, your first step is to draw the Lewis structure. Your second step is to figure out the formal charge on that element or compound. Now, why do we need to calculate the formal charges? So this is a polyanion, which is carbon, nitrogen, S minus. And I can draw for this structure, for this Lewis structure, two Lewis structures. And both of them, they have exactly the octet rule for each element, which is this one. This is the first Lewis structure that I can draw. This is the second Lewis structure that I can draw for this atom, for this molecular formula. Now, the formula charge is going to determine which Lewis structure is the favored one. So the favored Lewis structure, and this is a rule of thumb that you're going to be asked about. The favored Lewis structure is the one in which the atom's formula charge are closest to zero. In other words, your second step after writing the two Lewis structure or having those two Lewis structure is to calculate the formula charge for each atom inside that Lewis structure. And this is what I did. So I calculated, just to make it shorter so that we can go to cover more material. So I calculate the formal charge on nitrogen, which is the number of valence electron, minus in between two brackets, the number of lone pairs, plus half the bonding. And I get -1. For the carbon, the formal charge is 0. For the sulfur, in this case, it is 0. Now, in the other Lewis structure, the formula charge on the carbon is -2. That on a sulfur is a +2, and on a nitrogen, -1. So between A and B, A is the favored Lewis structure. In other words, this is the right Lewis structure. Why? Because in A, at least two of the atoms have 0 as a formal charge, while in this, none of them has a 0 charge. This is why I chose A over B as being the Lewis structure. And this is why, if you remember when we were doing the Lewis structure, somebody in the class asked me that day, okay, why we don't keep it this way, for example? Why we don't settle down with this Lewis structure compared to something like that? And the reason behind this is being wrong is that the formula charge on the carbon here is high, is not 0, while in this structure, the formula charge on the carbon is 0. And this is why whenever you see carbon with two lone pairs on there, know for sure that this is not the favored Lewis structure. It may comply with the octet rule that every atom in there have 8 electrons, but doesn't comply with the formula charge rule, which is that most of the atoms should have a formula charge closest to 0. Okay? So definitely this is why we don't consider that as the right Lewis structure. So the formula charge is going to be used when you have two Lewis structure and you're asked to pick which one is the favored Lewis structure. Knowing for fact that both Lewis structure comply with the octet rule, that means every atom, if we look to this one, every atom has 8 electrons, 8 electrons, 8 electrons. So if you look to the Lewis structure, it looks right. It is right, but what's going to determine which one is the favored one? That means in reality, in experimentally, we find it out there is the formal charge. Does that make sense? Okay. So this is why we use the formal charge. There is another reason that we're going to use the formal charge, which I'm going to talk about later on after resonance structure, after we talk about resonance structure. But this is one of the main things that we use formal charge for. Now, the next step is, okay, let's say I have carbonate. I want to draw the Lewis structure of this compound, and I'm going to do of this polyanion. So first of all, carbon going to be the central atom, the oxygen going to be 3 there. the total number of valence electron is 4 plus 3 times 6 plus 2 electrons equal, the total equal 24. I have 6 electrons in bonding. And the end of that is 18 electrons. I'm going to put 6 electrons on each. So 6 times 3, that's 18. And definitely I have to put 2 minus. Okay, now definitely all the oxygens have the octet rule, yet the carbon clearly doesn't have the octet rule. So now usually we say, okay, borrow 2 electrons from the terminal atom, which is in this case the oxygen. Now, okay, the choices are a lot there. I can borrow the 2 electrons from this oxygen, the blue oxygen, or the red oxygen, or the green oxygen. Which is the right one? They are all right, and that's the right answer. So all of these, whether I borrow those 2 electrons in here and I end up with this structure, where I have the red in here, two minus, or I borrow those 2 electrons or I borrow those 2 electrons from there. All of these are right. Guess what? The carbonate, if we look at the carbonate, if we have a carbonate and we're looking at the bonds of the carbonate, we'll find out that this carbonate anion is spending some time in structure A, sometimes on B, sometimes on C. And this is why we call all of these the resonance structure. And we call them resonance because it's exactly the same molecule, the same connection. The only difference between the 3 is where is this bond, where is those electrons, the arrangement of electrons. But it have exactly the same number of electrons, the same arrangement, the same geometry. The only difference is where is this bond. Okay, it may sound to you, okay, so what's she talking about? So what's the big deal about that? Resonance usually is this kind of thing, that the resonance is there, that we have more than one structure that this polyanion is in, usually stabilize the molecule. It makes its delta HF lower. That means the delta H formation, which we learned about in chapter 5. So it's make it more exothermic, the delta H formation more exothermic. And okay, let's see. So the other thing about this molecule, we're gonna find out when we talk about the bond length, that the bond length is a special bond length about this molecule, which we're gonna talk about in a minute. Now, how are you gonna figure out the resonance structure? So in this case, I simplify it for you and put it out there and said, okay, look, those lone pairs can be anywhere. But what if you have the Lewis structure like this? That means you already wrote the right Lewis structure, and you're asked to draw all the resonance structure. How does that take place? So usually the lone pairs in here on this, and now in this case I'm not borrowing. The lone pairs are going from this oxygen to be shared with this carbon, and that bond gonna break up and form 2 lone pairs. So, and usually the resonance structure, I refer to them that they are resonance by this double-headed arrow. And it's not this one. That's wrong. That doesn't mean resonance. That's equilibrium. That's nothing to do with the resonance. So usually the arrows that we put between resonance is a double-headed arrow. So with that in mind, The oxygen now gonna have those two lone pairs, and the lone pairs coming from this double bond that now is broken and it is two lone pairs. And the carbon, now those two lone pairs gonna form a double bond in there. And this is how I get the first resonance structure. Now how I get the third resonance structure, again the lone pairs in here gonna jump in here, and those lone pairs gonna, this bond gonna go to a lone pair. And this is that third resonance structure. So this is how we figure out that all the resonance structure, always a lone pair gonna go down, then a bond gonna break and form a lone pair. If you see yourself anytime doing that, a plus charge, for example, C plus, that you put this, that's wrong. That would never happen. A plus charge forming a bond, because a plus means there are no electrons in there, so that's wrong. Mainly, this is the main one, where a lone pair, you just get to form a double bond, and that double bond forms a lone pair. That's the most one that you're gonna see in this course. Now, another thing that I want to point out, remember that the atoms that can do double or triple bond are only carbon, nitrogen, sulfur, oxygen, phosphorus. So if you see yourself doing a double bond with a fluorine, that's wrong. Fluorine doesn't do a double bond. If you see yourself doing a double bond with iodine, with bromine, chlorine sometimes does double bonds because it's the period 3 and on, but fluorine, definitely you wouldn't see it having a double bond. Okay, so let's go to the next one. So this is just the definition of a resonance. So resonance structure is exactly represent the same molecule as the same number of moles, they have exactly the same geometry, the same number of atoms and type of atom. They only differ by the arrangement of electrons in that molecule, as we've seen a minute ago. Another example, and definitely its resonance stabilizes the molecules and lowers its energy, so its delta HF is more exothermic. Okay? Another example of resonance is the nitrate NO3 minus, this is the Lewis structure of nitrate. To go to the other resonance structure, again, I'll do the same. This lone pair gonna go in here, and this bond gonna go to that. So this is the first Lewis structure. Now the second Lewis structure is that those lone pairs in here and this bond break to form two bonds, and this is how I figured out all the resonance structures of this compound. And definitely okay? Does that make sense? Kind of? Okay. Let's do an eye clicker to see how we're going through this. So which of the following is a resonance structure of NO2 minus? stop it at 1:30. Okay. So I'm gonna stop it right here. I don't know how many you are here. So I'm gonna stop it right here and check what you think. And I have 85% B. B is the right answer. So the way that you would handle such kind of questions is first you write the right Lewis structure. If you don't have the right Lewis structure, I don't see how you're gonna get anywhere. So the first thing, nitrogen gonna be the central atom and the two oxygens right there. The total number of valence electron, nitrogen belongs to group 5, 2 times 6 plus 1. And somebody is talking when I'm talking. Jake, may you please figure out who's talking and take their ID number? 18, so we have total of 18 electrons. Now we have two bonds, that's minus 4 electrons in bonding. So we're left with 14 electrons, which I'm gonna put it 12, most oxygen, and here 1, and definitely I wouldn't forget that it is a minus. The Lewis structure is not complete yet because the nitrogen doesn't have 8 electrons. So now I have to decide to borrow. This is borrowing, that's not a resonance, okay? So this is gonna be, this is the Lewis structure. Lewis structure. Now how to figure the resonance? The resonance is if this two lone pair, the other resonance structure is if those two lone pairs get in here and this get there, and I would represent it with a double-headed arrow. So that bond now is this two lone pairs, and those lone pairs are there. So NO2 minus has two resonance structure, and clearly B is one of them. Okay? Any other one is not a resonance structure. Either, for example, A is not a resonance structure because it doesn't have the same arrangement. For this to be a resonance structure, it should have N as the central atom with the two oxygen, which is not the case. In addition, that actually it fulfills the octet rule, but it's not resonance structure. Now the last one is also not a resonance structure. The reason behind that it's not one of those, although it has the same arrangement of atoms, the same geometry, but it doesn't have the same number of bonds. So it should have exactly the same number of bonds, the same geometry, and it isn't one of the resonance. Okay? So this is how we figure out the resonance structures of different stuff. So what I'm gonna do is I'm gonna post kind of a worksheet on resonance so that you can do some more practice. The more you practice, the better. OWL has more also, so practice as much as you can on the resonance structures. Now, we're going to go to another topic which is much, much easier than the resonance and formally charged, so which is the bond order. And what is the bond order? So let's say I have C single bond C. So the bond order for a C single bond C for a single bond is the bond order is 1. And that's applied definitely for F single bond F, any two atoms, H single bond F, the bond order is 1. Now if I have C double bond C, the bond order in here is 2. So in other words, as everybody is figuring out that the bond order equal to the number of bonds between the two atoms. If we have 3 bonds or a triple bond in there, so the bond order is 3. Now, and this is the trend of bond order. I just have to tell you that resonance can have bond orders which is a fraction, and we're gonna talk about that in details in the coming slide. But keep in mind that the bond order of polycations or polyamine or compounds that resonance can be a fraction. So it can be 1.5, 2.5, 3.5, 3/4, 3.5. So it can be a fraction. So let's see. So the bond order usually is I should say here, affects. The bond order affects rather than proportional. Affect two important properties of bond properties. So the bond order determines the bond strength and the bond length. And they are two very important properties for any chemical that we talk about. The bond length and the bond strength, and both of them, they depend on the bond order, or they are affected by the bond order. So let's start with the bond length. So in this case, the bond order between carbon and oxygen is 3, the bond order. In this case, the bond order is 2. And in here, the bond order is 1. And these are the lengths of those bonds in each of these cases. So take a minute and look at the numbers. As the bond order is increasing, is the length decreasing or increasing? So clearly, as the bond order is increasing, the length is decreasing. And this is, by the way, picometer, which is 10 to the minus 12 meter. Okay? So as the bond order increases, the length of the bond decreases. And this is a rule of thumb. So if we're comparing, in this case, the 3 elements is carbon, oxygen. In the 3 cases, the atoms are carbon, oxygen, carbon, oxygen, carbon, oxygen. The only difference in there is the bond order. So the higher, or as the bond order increases, the length of the bond gonna decrease. And that's a rule of thumb. So this is the first property, which is the bond length, which is affected by the bond order. Okay. Now let's see how would the bond length be affected. Let's say in this case I have HF, HCl, and H iodine. So in all of these cases, the bond order is 1. Bond order 1. The bond order is 1. And the bond order is 1. So the numbers that are there are in picometer, and they represent the length of the bond in each case. So if in the case before, in the slide before, the atoms were the same, carbon, oxygen, carbon, oxygen, carbon, oxygen. In this case, one of the atoms is changing in this case. This is HF, HCl, HI, but the bond order is the same. So in this case, what's affecting the bond length is the size of the atom. So the size of the bonded atom will affect the length of the bond. Since iodine is bigger than chlorine than fluorine, because if you remember, as we go down the group, the radius increase. So that clearly tells that iodide is bigger, or the iodine is bigger than Cl than F, and that's affecting the length of the bond. So the atom, if we're comparing bond length of 3 different atoms, the atom size, the atom radius gonna affect the length of the bond. Okay? And this is the case, and this is the other case. So if we have If the bond order is increasing, definitely the length will decrease. If we're talking about the same bond order, we're comparing the three compounds with in the same bond order. Now we have to look to the atom. If it is a different atom, if the atom is bigger in radius, that implies the length of the bond gonna be bigger. So that's for the bond length. Now let's do an unclicker about that, and it is gonna be numeric. So, which diatomic molecule would you predict to have the longest bond? I'm going to stop it at 130.
We're going to get to the end of the PowerPoint today. It's looking too crazy now.
So I'm going to stop it right here to check what we know. And I have 3 to be 48%. 3 is the right answer, yet the percentage is low. So, the way that we handle such kind of question is your first step is to draw the Lewis structure. Because you want to figure out the bond order, because the bond order affects the length of the bond. So your first step is the Lewis structure. So this is the Lewis structure of nitrogen. This is of oxygen. And this is of fluorine. So clearly the bond order is 3, 2, 1. And we said that the bond order is inversely proportional to the length. That means as the bond order increases, the length will decrease. The question is asking me about the longest. So that's going to be the longest bond because it has the lowest bond order. Because it has the lowest bond order. Okay. Now let's go to another topic. So now we've done from the bond length. We're going to talk about bond strength, which also depends on the... okay, so before we go any further, we have to talk about... We talked about that the bond order and resonance structure can be a fraction. So how we can calculate the bond order in a resonance structure? So first of all, the way that chemists figured out that there are resonance structures out there is by one of the molecules like carbonate. And what they did is they were trying to figure out, first of all, they measured the delta H formation. They found it way more exothermic than the tabulated one. So that was their first clue. Their second clue was they were trying to measure the length of the bonds. And they know that the carbon-oxygen bond, single bond, is 143 picometer. And the C double bond O is 122 picometer. But when they measured the length, or they calculated the length of the carbon-oxygen bonds inside this carbonate, they find out all these three, 1, 2, 3, and even the fourth one, all of them equal to 129 picometer. So it is a number in between a single bond and a double bond. And that was one of the clues that there is something going on. And what's going on that, do you remember that we have a 3 resonance structure? We just talked about it, that the double bond can be either here or there. Those 3 resonance structure. So it happens that this polyanion can be in the 3 forms of the resonance. And this is why the length of those bonds is in between a single and a double bond. And the reason behind it is that the bond order in the resonance structure is not 1, is not 2, it's something in between. And the way we calculate the bond order in resonance structure is by equal to the number of bonds involved in resonance over the number of resonance structure. Okay, what does that mean? Let's do an example, which is this one. How many resonance structure carbonate has? We just did that. 3 structures. So 3 resonance structures. How many of those bonds are involved in resonance? It's 1, 2, 3, 4. These 4 bonds are involved in this whole resonant thing. So the bond order equal the 4 bonds that are involved in the resonance over the number of resonance structure, which is 4 over 3. So the bond order for this resonance structure is 4 over 3. It's not 1, it's not 2, it's not a 3, it's something in between, which is 4 over 3. And this is why the length of the bonds in resonance structure is in between the two, in between a single bond and a double bond. This is how we calculate the bond order in a resonance structure. Okay, and the bond length is going to be in between those two values. We're going to do more eye-clicker on that, how to calculate the bond order and how to figure all of this in a minute. Okay, which is right now, not even in a minute. Okay, how many equivalent Lewis structure are there for NO2Cl? Another way is asking you how many resonance structure, because a resonance structure is an equivalent Lewis structure. So when they ask you equivalent Lewis structure, they mean resonance structures. Are there for NO2Cl? And what is the average NO bond order? Stop it at 2 minutes. Okay, so I'm going to stop it right here and check what you think. So send your answer. Not here. Okay. And I have 50-50 for A and B. And the minimal for the others. The right answer is A. And yes, it is one of the hard questions that you're gonna deal with in this course. So your first step when I ask you about a resonance structure, the right track is to draw the right Lewis structure. And from there, figure the resonance structure, then calculate the bond order. So the first thing I'm going to start with is nitrogen going to be the central atom, which is because it's lowest electronegativity. The total number of valence electrons, I have 2 oxygens, 1 chlorine, and 5 for nitrogen. That's going to end me up with 24 electrons minus 6 electrons in bonding. So I'm left with 18 electrons, and I'm going to put in the terminal atoms. Yet the nitrogen doesn't have enough electrons, so I'm going to borrow those two. Because chlorine doesn't do double bonds, it would do only a double bond if it is in a hypervalent compound. That means it is the central atom, which is not the case in here. So the right Lewis structure is NO and the Cl. So that's the Lewis structure. Now, the second question is the other resonance structure. The other resonance structure, if this lone pair goes down and this bond be a lone pair, and that's going to resonate with this one in here. And the Cl. Now, definitely the Cl wouldn't share its electrons and form a double bond because it's not the CNPOS that they usually not carbon, oxygen, nitrogen, phosphorus, sulfur. Again, it only does, or chlorine only does a double bond if it is the central atom in a hypervalent compound. That means it's going to have 12 electrons or 10 electrons above the octet. So those are the only two structures, so two resonance structures. Now the bond order. So the bond order equals to the number of number of bonds that are involved in resonance, and those are 1, 2, 3. Why I didn't include the Cl1? Because it's not involved in resonance. Because it's not, the lone pairs of chlorine wouldn't go there and the double bonds come up. This is why the number of bonds that are involved in resonance is 1, 2, 3 in this case. While in the carbonate was 4 of them because the double bond was going from one to the other to the third, from the first oxygen to the second to the third. So it is 3, that's the number of bonds that are involved in resonance, and over 2, which is the number of resonance structure. So that implies A is the right answer, which is we have 2 resonance structure and the bond order is a 3 over 2. What is your expectation for the bond length of nitrogen, oxygen inside this resonance molecule? Is it going to be equal a single bond NO, a double bond NO? Somewhere in between. Thank you. So the bond length in this is going to be somewhere in between the two. Okay, so let's see what we have next. Now we're going to talk about the second thing, the second factor that is affected by the bond order, which is the bond dissociation energy. And the bond dissociation energy is the energy that I need to break a bond. Okay, so simply let's look to those 3 numbers in there, those 3 examples. As you can see that breaking a single bond needs less energy than breaking a double bond than a triple bond. And I think that makes sense to you. If I have 1 bond to break, definitely it's going to be easier than having 2 bonds to break, than 3 bonds to break. So as the bond order, the greater the bond order, because in this case the bond order is 1, here it's 2, here it's 3, the bond order. So as the bond order is increasing, the higher the strength of the bond, and that makes sense. And the shorter is the bond. Remember that as the bond order increased, the length would decrease, but the bond strength is going to be a stronger bond to break. And this is a rule of thumb that you should always keep in mind, that the bond order affects both the length and the energy and the strength of the bond. So the higher the bond order, the stronger is the bond, and the shorter is the length of the bond. And I'm gonna stop right here, and happy Thanksgiving, and I'll see you Monday.